Okay, here we continue our discussion now. This is actually part two of stainless steels, but actually part three of the whiteboard lecture series on metal alloys and heat treating. We'll get to heat treating if we have time on this one at the end. But let's pick it up where I left off last time. Talking stainless steels, that miraculous metal, the crowning achievement of metallurgy, all that. And there's basically three types, what we call grades of stainless steel. There's not just one type. And the three types are called ferritic, martensitic, and austenitic. And of course, you're very familiar with those terms based upon the iron-carbon diagram and also the IT diagram for this microconstituent product called martensite. Well, let's go over a little bit of the generalities here. And for the most part, all stainless steels have fairly low carbon content, usually no greater than 1%, but they can get a little higher, especially obviously on this one. But generally speaking, they have fairly low carbon contents. Where the properties come into effect are with the alloying of specifically chromium and also nickel. When combined, that's where stainless steels really get their enhancements property-wise, mechanical property-wise. Okay, so real quickly, ferritic, it's non-hardenable. Has of all the other two stainless, there's less carbon, less than 0.2%. It is magnetic. Now, you might find this interesting because the most stainless steels you're familiar with are non-magnetic. But actually, there's only one grade that is magnetic. The other two are magnetic, and of course, ferritic is one of them, and the other magnetic is martensitic. So, at any rate, it's poor weldability, not really used in that application. And it's always used in an annealed, what we call a softened state. And again, its chromium content, has to be greater than 11, and it usually ranges from the 12 to 18%. Now, more importantly, really, as far as usage goes, martensitic is widely used, and specifically because it is the only stainless steel that is truly hardenable by heat treating methods. All right. And again, carbon, because it is heat treatable and can be thoroughly hardened, it has carbon up to 1.2%, which is quite a bit. And it is magnetic. Again, poor weldability. And it's most widely used in all different types of surgical instruments, medical instruments, all kinds of knife blades. If you have a stainless steel knife blade, I promise you it's going to be a martensitic grade. And of course, this is where hardness and the hardness and anti-corrosive properties are at a premium. That's where you would be seeing the uses of martensitic. Now, stainless steels, stainless steels have a completely different designation numbering system than standard plain carbon steels, and they're just three numbers, and usually they're in the 400 and 300 ranges. And of the martensitic, the most widely used of the martensitic grades is the number 410. If you ever see that number, that's usually the most widely used one in martensitic applications of stainless steel. And again, its chromium content similar, obviously the same as the ferritic at 12 to 18%. Okay. Austenitic, we should put a big asterisk here because without a doubt this is the largest usage of all stainless grades are the austenitic. I should put a little asterisk here. There you go. By far the most widely used. But it is non-hardenable, all right? You cannot harden it by heat treating methods, but as I mentioned to you earlier, it can be work hardened. And sometimes that's a blessing, and sometimes it's very, very negative. So as far as cold working, work hardening, cold working, same thing. So we have to be cognizant of that when designing and using this type of material. It is non-magnetic, the only grade that is truly non-magnetic. It has without a doubt, the best corrosion resistance of all these other stainless steels. Very easily welded, so the weldability is good. It has excellent resistance at both high and low temperatures. Now look at these temperatures, and this is continuous service, by the way. Some grades are up to 1700, and others are even up to 2100 degrees Fahrenheit. That's why I was telling you earlier in the first video, is that this is probably the most widely used property inherent to stainless steels of why they are used in so many different types of industrial applications. Not necessarily just for their anti-corrosive properties, is its elevated temperature applications. And without a doubt, it from a fabrication standpoint is the best fabric capability of all the other stainless steels. Okay, so that's why it's used so much. Now, the most widely used numbering grade of these stainless steels is what we call a 304 stainless, and it's also sometimes you hear it called 18-8, which just means it's got 18% chromium and 8% nickel alloyed together. And you'll see this used everywhere. In so many different applications where traditional standard stainless steel is utilized. Okay, but look at this. The chromium content is way up there, obviously, since it has the best corrosion resistance, way up there between 16 and 26% chromium. Okay, that is very significant in and of itself right there. Okay, so these are all the stainless steels. Great products. I used them a lot myself when I was working in industry and designing these commercial food processing equipment. Also, that's all we did use was stainless steel. So I had a lot of experience both designing and learning how the fabrication processes worked on these stainless steels. Okay, so now what I want to do is I want to commence or talk a little bit about some of the basic heat treating principles and treatments. So it'll require me to erase this. And normally in class I would pass around samples of stainless steel grades, but really can't do that here. Okay. All right, so now what I want to talk about are some heat treatments. All right, the basics of heat treating, essentially, is what I want to talk a little bit about. And so let's look and see what we got here as far as heat treating. So this is all going to be about principle. Heat treatments, or principal heat treating, or all right, okay. Now, first I think we kind of need to define what heat treating is. All right, and it can be defined as the controlled application of time, temperature, and atmosphere. Remember we talked about oxidation here earlier. To produce a predictable change in the internal structure, what we know to be the microstructure of a metal alloy. Okay, so that's what heat treatment really is. And let's go over the principal heat treatments as we know them. There are really three, although there's actually two. Hardening. So let's list these as hardening. All right, and then softening. Okay, and under hardening, we're going to have two different types. We're going to have something known as through hardening. Through hardening, okay? This is where the martensite formation through the entire cross section. In other words, all the way through its core, to its core. All right. Now, then we'll talk about that. Now, sometimes this is also called deep hardening. All right. Now, the other one is, and we've mentioned this before in class earlier, back sometime in January, is surface hardening. Surface hardening, okay, and these are classified as diffusion treatments. All right, and this is sometimes referred to as also case hardening. All right, sometimes you hear it called that, and the first thing is a process called carburizing, and we've had this before too. Carburizing, which basically we're just diffusing into the surface of a low carbon steel more carbon to it, so it has a chance to be surface hardened. So carburizing has to take place, and there's really two ways to do this. You can do it through what we call a pack or dry hardening. Carburizing, and there's two ways to bring that temperature up, because all hardening processes, as we've talked about, start at the austenitic temperature range. So you can do that with either a flame, or you can do it electrically through what we call induction heating. And if you looked at that video, and I hope you did, on heat treating, I mean, that really brings home what these processes are, because they showed some specific applications of doing gears using both flame and induction hardening. So I really hope you looked at it. If you haven't looked at it, you really need to watch it. It's an excellent video. It'll really help put things in perspective, I think. The other way you can carburize things is through gas treatments, which we know as, most of them are just called nitriding, and sometimes carbonitriding. All right, and there you just take and encompass that part in a very highly carbonaceous, or in this case nitrogen, which does the same process. And what I wanted to show you real quickly are samples of what these look like. Okay, we talked about them in class, but here's a good sample of a basic pack carburizing. Let's see if I can get this up a little bit bigger for you. But here's a good example of a pack carburizing. You've got this part in here, and then you've packed it with obviously some kind of highly carbonaceous material like charcoal, coal, coke, something like that. And then you add temperature, of course. We know it's a heat. It's a thermally derived process, so we have to add a little bit of heat to start the diffusion process. And so we're taking a low carbon piece and diffusing into it a certain amount. So obviously it's going to be dependent upon the temperature of, as far as how deep this goes, how the temperature and how long it stays will determine the actual depth of hardness that this part will have. Okay, so that's a good example of a pack carburizing, and here's another example of or example of the gas type. Here we're using ammonia, which has a lot of nitrogen in it, of course, and basically pumping it into this closed apparatus here with a workpiece. And good thing about these treatments is it doesn't really involve any heat, so there's not much chance for distortion, etc., etc. So it's a good way to do it, and you get a very, very hard surface without any kind of distortion probabilities. Okay. Now, let's go back to full screen. All right. Now, let's look at softening processes, and the timer just went off, but the softening processes basically can be lumped together as we've already talked about annealing processes. Okay, annealing processes where we're usually taking something that's been overly cold worked and then restoring to it some of its more some better properties, ductility, toughness, that kind of thing. We talked about that back when we were looking at that with respect to, we have a recovery, a recrystallization, and then grain growth. Those are the three stages of annealing process. And then the other one that we talked about when we were talking about the isothermal diagram was martensite, because when we achieve the martensitic structure, although it's very, very hard, it's very, very brittle, can't really be used. So martensite is always used in its tempered state. So tempering is another type of softening process. All right, and that's where you just take and reintroduce that part after it's been quenched very quickly, and then put it back in a furnace about 350, 400 degrees or so, and go through that to soften it some and to bring back some of those properties that would enhance it as far as being usable. Okay, so again, this whole hardening process, I'm run out of space here, but this whole, as I told you, as we talked about before, it's two steps process, and austenitizing, and I'm running out of ink on this one, so switch pens right quick. Heat treating process. It's a two-stage. First, you're bringing it up to what we call austenitizing it. Austenitizing temperatures. All right. And we do that, of course, and that's going to be, roughly plus 50 degrees Fahrenheit over, usually it's A3, the upper transformation A3 or ACM lines on the phase diagram. And of course, the reason we do that is because austenitizing brings it up to an FCC structure, which we maximize the carbon content, which is what we're trying to do, maintain that carbon content when we heat treat it so it can be hardened. All right, and the second step, of course, is a rapid cooling, or something we call quenching. And basically we have three different types of mediums. Brine is one, water is another, and oil is the least aggressive of all those. So those are the two basic steps in there, and so that's what we're going to be. That's how these heat treating processes work, and we're now going to start the next video. It's going to be completely involved in talking about hardenability. Okay, all talking about hardenability, and we have done this. We have talked about this repeatedly. Kind of very similar to what the alloying elements were used for, but there are logical reasons why we heat treat. And let me write those down here for you right quickly. And they usually usually heat treating is used to enhance the mechanical properties. All right. And of course, tensile strength is affected by that. Ductility is affected by that. Impact strength is affected by that. Sorry about that. Impact strength. And then, of course, by far, hardness. Okay, so those are the basic mechanical properties that are affected and or enhanced by heat treating. Okay. Now, so we'll stop here and we'll pick it up. I'll put out another one in the morning. We'll finish this up because we are scheduled to have an exam this Thursday on 4/23, and we'll try to start that at regular class time at 9:30. But I'll talk to you more about that in the morning when we do the next video.